In this video, we are going to discuss chi-square tests. During our previous topics, we have encountered the use of the chi-square table. So the following tests that we will discuss in this video will involve using the same chi-square table. And that is why we call these chi-square tests. For these chi-square tests, we normally want to test whether a certain set of values follows a certain distribution, or if they follow a certain set of values which we call as the expected values. There are three applications that we are going to discuss, and you will see later on that these applications are quite similar to one another. So these are the goodness of fit test, the test for independence, and the test for equality of several proportions. For any of the three applications that we are going to discuss, we will be using the same chi-square test statistic, which is given by the following formula. So the chi-square test statistic is equal to the sum of the observed minus the expected value, which is squared, and divided by the expected value. So again, O sub I refers to observed values, while E sub I refers to the expected values. So we are just getting the square of the difference between the observed and the expected values, dividing that by the expected value, and then taking the sum over all such pairs of observed and expected values. You will see later on when we solve the exercises how this formula is applied. Next, for the critical region, for any of the chi-square test statistics that we are going to discuss today, the rejection criteria is given by chi-square greater than chi-square alpha, while the degrees of freedom to be used will depend on the application. So we will show later which degrees of freedom to use for each application. So to illustrate, we start with the goodness of fit test. So this is the first application. And in goodness of fit tests, we want to test if the data follows a specified distribution. Our null hypothesis assumes that the data observed follows the specified distribution, while for the alternative, the data does not follow the specified distribution, meaning there is a significant deviation from the distribution that we are trying to test. For this particular application, the degrees of freedom is given by k minus 1, where k is the number of cells or columns. We will see later what we refer to as the small letter k. So as an example, consider the experiment of tossing a 6-sided die. We wish to test if the die is balanced. That is, that the distribution of our data is uniform. So if the die is balanced, we would expect the same number of times that the numbers 1, 2, 3, 4, 5, and 6 appear. So if we toss the coin 120 times and obtain the following data, we want to test if the die is balanced using a 0.05 level of significance. So again, if you toss the coin 120 times, then you would expect that each of the numbers from 1 to 6 would appear equally. So that means each of these numbers would appear 20 times, which is why in the expected row, all of the expected values for each of these numbers is 20. And then for the observed row, these are the actual observations when we toss the coin 120 times. Sorry, when we toss the die 120 times. And we saw that the number 1 appeared 22 times, the number 2 appeared 18 times, and so on. So given these observed tosses or observations for each of these numbers, does this indicate that the die is balanced? So using the null and alternative hypothesis that we mentioned in the previous slide, we can use the following as our null hypothesis. We can use the die is balanced, or we can say that the distribution of die tosses follows a uniform distribution. For the alternative, we might say that the die is not balanced, or that the distribution of die tosses does not follow a uniform distribution. So applying again the steps of hypothesis testing. So for step 2, we have alpha equal to 0.05. For step 3, we reject HO if the chi-square test statistic is greater than chi-square alpha. In this case, our alpha is 0.05, and we will be using 5 degrees of freedom. So in this case, our K is 6, since we are testing 6 particular columns, 1, 2, 3, 4, 5, 6. 6 minus 1 is 5, so we are using 5 degrees of freedom. So if we look for the critical value with 0.05 alpha and 5 degrees of freedom, you should find a chi-square, the value in the chi-square table to be 11.070. So this is now the critical value for our goodness of fit test. Next, we now compute the chi-square test statistic. We said that the formula is given by the following. So the sum of observed minus expected squared all over the expected values. So to show how this is computed, you just go through each of the possible columns or cells and get the difference of the observed and expected value, square, and divide by the expected value. So for the first column here, the observed value is 22. And the expected value is 20. So you have 22 minus 20, get the square, and divide by the expected value, which is again 20. Moving to the next cell, you now have 18. Okay, and then you subtract the expected value, which is again 20. This is 18, and divide by 20. And so on. So you will be doing this for each of the 6 cells until you reach the sixth cell, which is also given by 18 minus 20 squared divided by 20. By doing this computation, you can check that the answer you will get is a chi-square value of 1.1. So given that the chi-square value is 1.1, comparing with the critical value of 11.07, it does not exceed the critical value. So our conclusion is to not reject the null hypothesis. So there is insufficient evidence to suggest that the die is not balanced. So as you can see, from the observed values, there's no significant deviation from 20. No? So there is no number that appears significantly more times. Okay, so you might say that there is a significant difference if, let's say, the number 3 appears 30 or 40 times. But in this case, you might see that the distribution of the values is quite close to being 20 each. Okay, so we failed to reject the null hypothesis. So in all of the applications that we will discuss in this video, we will be applying this same formula for the test statistic. So take note of this: observed minus expected squared all over the expected value. And you just need to identify which are the observed values and which are the expected values. So for the next application, we call this the test for independence. We want to test whether two variables are independent of one another. In other words, we want to test if one variable has an effect on another variable or if these two variables are independent. Our null hypothesis is that the two variables are independent, meaning they have no effect on one another, while the alternative is that the two variables are not independent. For this particular application, the degrees of freedom is given by r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. Finally, to arrive or to compute the expected values, we will use this formula, which is row total times column total divided by the grand total. And we will again illustrate how to apply this in the next example. So suppose we want to test if the presence or the absence of hypertension is independent of one's smoking habits. We obtain the following data from a sample of 180 individuals. So we see that there are 21 non-smokers with hypertension. There are 36 moderate smokers with hypertension, and so on. Given this data, we want to test if the presence or the absence of hypertension is independent of a person's smoking habits using a 0.05 level of significance. So again, for step 1, identifying the null and alternative hypothesis. The null hypothesis is that the two variables are independent. So hypertension is independent of smoking habits, while the alternative is that hypertension is not independent of smoking habits. For step 2, we have alpha equal to 0.05. For step 3, we reject HO if the chi-square test statistic is greater than chi-square of 0.05 and the degrees of freedom is r minus 1 times c minus 1. In this case, you have 3 columns and you have 2 rows. So 3 minus 1 is 2 and 2 minus 1 is 1. So 2 times 1 is 2, meaning we will be using 2 degrees of freedom. Okay, so again, you have 3 columns, minus 1 is 2. You have 2 rows, minus 1 is 1. So 2 times 1 is 2. And referring to the chi-square table, you will see that this critical value is equal to 5.991. For step 4, before we compute the chi-square test statistic, we first need to identify what are the expected values for each of these cells. So I will recreate the table here. You have the non-smokers, moderate smokers, heavy smokers, and we need a total column. While for the rows, you have those with hypertension and no hypertension. And again, you need a total row. So non-smokers is 21, 36, and 30. If you get the row total would be 87. Next, for those with non-hypertension, you have 48, 26, and 19. And the row total would be 93. Finally, getting each of the column totals, you would have 69, 62, 49, and a grand total of 180. So all of the numbers that we see here are observed values. In order to find the expected values, we need to use the formula that the expected value is equal to the row total times the column total divided by the grand total. So for example, for the first cell, we will be multiplying the row total, which is 87, by the column total, which is 69, divide that by 180. Okay, so again, 87 times 69 divided by 180. That will give you 33.35. Moving to the next cell, the row total is still 87, while the column total is 62. So you multiply 87 times 62 and divide by 180. That will give you 29.97. Moving to the next cell, you have 87 times the column total, 49, divided by 180. That will give you 23.68. Moving to the next row, the row total is 93 times the column total of 69. So 93 times 69 divided by 180 would be 35.65. Next, you have 93 times 62 divided by 180, which would be 32.03. And finally, you will have 93 times 49 divided by 180, which is 25.32. So everything that you see in green, those are now the expected values. So now, since we have observed and expected values, we can now compute the chi-square test statistic. Going through each of the cells. So for the first cell, you have an observed value of 21 minus the expected value of 33.35 squared and divide by 33.35. Going to the next cell, you would have 36 minus 29.97 squared and divide by 29.97. And so on until you reach the last cell, which would give you 19 minus 25.32 squared all over 25.32. So you can try to verify that the chi-square test statistic would be equal to 14.4644. So comparing the chi-square test statistic with our critical value of 5.991, we see that the test statistic exceeds the critical value. So therefore, we reject the null hypothesis, and hence hypertension is not independent of smoking habits, meaning there is a significant relation between the two variables. So as you can see, for the non-smokers, there is a higher percentage of people with no hypertension, while those who are heavy smokers have a higher percentage of people with hypertension. So that is what we mean by these two variables being not independent of one another. Finally, for the last application, we have the test for the equality of several proportions. So we just want to test if the proportion of success is equal for more than two populations. In other words, our null hypothesis is equal to P1 equal to P2 equal to up to P sub K, wherein you have K populations, and you want to test the equality of all population proportions of success. While the alternative is that there is at least one pair among these population proportions which is not equal. In terms of the methodology, this is exactly the same as the test for independence, except that the number of rows is always equal to 2, since you only have two possible options, either a success or a failure. Therefore, the degrees of freedom is just k minus 1, where k is the number of populations. And again, the expected values are computed as the row total times the column total divided by the grand total. So the last application will have a different null and alternative hypothesis, a different application or purpose, but the methodology is quite the same as the second application. So in this example, we have a set of data collected to determine whether or not the proportion of defectives produced by workers is the same between 3 different shifts, the day, the evening, or the night shift. The following data were collected. So you have 3 different shifts, and we compute how many defectives were obtained from each shift. Using a 0.025 level of significance, we try to determine if the proportion of defectives is the same for all 3 shifts. So before you proceed with the video, I encourage you to pause for a while and then try to solve using the same methodology as the second application. Okay, so once you have tried to solve this problem, you may proceed. I will be showing just the solutions for this particular example. So I encourage you to pause the video first. Once you are done with trying the problem, you may unpause, and the following is the solution. So for the null hypothesis, we have P1 equal to P2 equal to P3. We only have 3 populations since we are comparing the proportion of success between 3 shifts. And for the alternative, we have the alternative that at least one pair of proportions is not equal. Our level of significance is 0.025. We reject the null hypothesis if chi-squared is greater than chi-squared 0.025 with 2 degrees of freedom. So you have 3 populations in this problem. 3 minus 1 is 2, so you have 2 degrees of freedom. And referring to your chi-square table, you will find a critical value of 7.378. For step 4, try to check if you will get the same table as the one shown here. So the numbers in parentheses are the expected values. Again, just do the computation of the row total times the column total divided by the grand total. And applying the formula for the chi-square test statistic, you will arrive at a chi-square test statistic of 6.2339. This value does not exceed the critical value of 7.378. Therefore, we fail to reject the null hypothesis. There is insufficient evidence to suggest that the proportion of defectives between the 3 shifts is not the same. So in other words, the proportion of success between the 3 shifts is not significantly different from one another. They are quite the same. Upon checking with the test of equality of proportions or the chi-square test. So this is where our video ends, and I hope you understand the application of the chi-square tests.